This program exists with the hope of helping visualize a world with 4 spatial dimensions. There are some models freely rotating in here. Now, normally when a fictional world or a game, virtual reality, whatever is written with 3 dimensions, people are used to viewing depth or perspective of the 3-dimensional world with 2 dimensions in the screen, up, down, left, right, and a perpendicular dimension in and out of the screen. And that perpendicular dimension is used to decide what is in front of what. You don't draw something on top of an opaque object if it is behind that object, for instance. Well, in this case, if there's a 4th spatial dimension, there's like a second depth dimension, which is perpendicular to not only the screen, but also that usual dimension that is also perpendicular to the screen. To have them all perpendicular to each other is a lot easier to do mathematically and write it to a computer and tell it what to do than it is to try and just visualize it as a person. So this program does quite a nice job as far as I can tell. And the reason there is a hint as to what's going on with the extra depth dimension is that I've told the computer that if the depth dimension is 0, that is where you transition from maximum green in the color to no green. So you see all these little slashes or slices going through all the figures that are really bright and then really dark, transitioning. That is when the component of that extra depth dimension changes sign. It goes from positive to negative or vice versa. So the models are passing through that. And you can see the small tesseract is almost entirely pinkish. And then if I move it back there, all of a sudden it starts passing through and starts to turn green again. So that's preferable, at least in my opinion, to taking a 3-dimensional slice, because if you did that, the only part you'd be able to see is where it transitions. So now that tesseract would be entirely invisible. It would just be because it's only on one side of that slice, that 3-dimensional slice. Now it's passing through it. So you can see the green parts going through it, and then it's invisible again. So that explains why in a program like Miagakure, which is wonderful in its own right as a puzzle game prototype, I'm not sure how far along its progress is, it takes 3-dimensional slices. So you'd see objects like that passing through and appearing to change shape when they actually don't, because it's like an MRI scan. You're taking different cross-sections of the objects. There is another nuance with this particular program, which is that this is actually using hyperbolic geometry. So if I travel away from everything, it appears to shrink off exponentially until it does not occupy a single pixel. Fortunately, I can just bring it back, just travel the opposite direction so that I don't get lost. Another nuance with hyperbolic space itself is that there's a preferred unit. In Euclidean space, it doesn't really matter if you measure in meters or feet or kilometers, but you can actually see it pretty well with those tesseracts. The much larger tesseract, you can see that cube that's drawn, that appears to be drawn in the middle. When you project down from 4 dimensions into 3, there's that part in the middle that appears to be much smaller than the outside part. And that is because of the exponential decay of apparent size in hyperbolic space. Whereas the smaller tesseract, that effect is much milder. They can rotate to get a better view of those tesseracts. Yeah, see. So there appears to be a small cube in the middle of the smaller tesseract, but it's larger in comparison to the entire figure than what you see for the big tesseract. In Euclidean space, you could just move really far away, and the front and back sides would appear very similar in size because the perception of distance only drops off in a polynomial sense rather than exponentially. So eventually the relative sizes of front and back would appear almost the same, Just as if you view something like the Earth from an infinite distance, you can easily see half of it or almost half of it. But in hyperbolic space, it just occupies a very small section of the view. And each time you step away by another unit, that section of the view drops off by a factor. It doesn't decrease slowly, it decreases very quickly. Yeah, this is a really complex looking shape, but I'll come back out of it. And that's actually the same shape. So this is a 4-dimensional model of a 5-dimensional figure. It's not actually a 5-dimensional figure because this world only has 4 spatial dimensions. You can't actually build a 5-dimensional model in it. But it is the dual of the 5-dimensional hypercube. So it's called a cross polytope. Maybe you should just go through it a little further. There we go. Sometimes you need to rotate a different way to get things back into view. And that's another thing about having 4 spatial dimensions, is that the mouse alone and WASD do not suffice. There are more degrees of freedom. So I've integrated toggle keys to change which degrees of freedom the mouse and the usual keys for movement are applying to. I'd rather do that than have more extra keys. There are only 2 extra keys in this program. There we go. So I can get back to the other figures. Yep, there are a total of 8 models, not counting, it's the same shape. And as I've mentioned, it's not quite the same shape. The fact that the tesseracts are, they're still regular tesseracts. And in Euclidean space, the angles and ratios of side lengths, if you scale a figure by a given, 2 times larger or 3 times greater in dimensions, the angles and proportions stay the same in Euclidean space. But as you've seen with these 2 tesseracts, where one cube on the inside, which is not actually on the inside, it's rear and front instead of inside and outside, because of projecting from 4 dimensions to 3. The rear one appears so small when the tesseract is large, but not so much for the small tesseract. Objects that you would think would have the same shape, in general they have the same shape. They have the same construction, the same number of cells, edges, vertices, things like that. But they're not similar as similar triangles would be in trigonometry. There we go. I'm trying to center on the figure over there. Here we go. Yeah, there. That's the fun part. There's a way, this particular degree of freedom of rotation for the camera, it looks like not much is happening, but that's one of the main purposes of encoding that extra dimension of depth into the green, because the objects appear to go in and out in a similar way. They appear to pass through themselves, but they appear to follow similar trajectories. And they're not quite. You see the other shape on the right, not the tesseract, but the one that's just passing off the corner of the screen there. When I come back on this side, it comes back in. So you can see that the objects kind of exchange positions. But if you're just looking at the 2 in the middle, they just pop in and out. But what that green component is telling you is that they're on one side of the 3-dimensional slice and now they're on the other one. And as they get further and further from the meeting point, the green starts to go away from that 0 or maximum. So here they're really dark pink, and then they lighten up a little bit as I come away. So yeah, it's not just all or nothing. There needs to be some indication of how far away they are from that section. For now, that pretty much sums it up for this program. Thanks a lot for watching.